costly upkeep, and being superseded by newer generation of stealth aircraft. As the Have Blue program progressed, Northrop began working on a technical demonstrator of its own, known as Tacit Blue. Tacit Blue attempted to demonstrate a series of then advanced technologies, including forms of stealth that employed curved surfaces and the use of less radar reflective composite materials. During the late 1970s, due to the success of the Have Blue and Tacit Blue programs, momentum was building for the development of a deep penetrating stealth bomber. By 1979, the highly secretive Advanced Tactical Bomber program was started, under the code name of Aurora. With the recent development of more advanced supercomputers, superseding what was available during Echo 1's development, more complex radar cross-section calculations could be performed, allowing for the design and analysis of blended curved shapes. Northrop would eventually win out as the best design choice with their flying wing design. With no protruding vertical surfaces, the flying wing design forms a near-perfect stealth shape, offering no angles to reflect radar with. An added benefit to this design is the inherently small visual silhouette of the airframe, creating visual stealth as well. Adding to this, the majority of the aircraft was made of radar-absorbing carbon graphite composites, with parts being covered in radar-absorbing materials. Internal structures of the airframe are also designed to trap radiation. Similar to the F-117, the engines were buried deep within the frame, hiding highly reflective rotating engine components. To reduce its infrared signature, the engines are mounted above the wings, masking the exhaust. Additionally, cool air is injected into the exhaust flow, further reducing its heat signature. Circulating cooled fuel is also used to cool exhaust sections of the aircraft, as well as leading surfaces of the aircraft that are heated by air friction. Additives are also dispensed into the exhaust stream in certain conditions to eliminate contrails. Designated as the B-2 Spirit, this flying wing design also offered efficient aerodynamics, giving it a range of 6,000 miles. However, with no vertical surfaces, it requires fly-by-wire computer control to maintain stability. The B-2 became fully operational in 1997, with its combat debut occurring in 1999 during the Kosovo War. Its stealth and incredible range has allowed the B-2 to take part in some of the longest bombing missions ever during Operation Enduring Freedom, with some exceeding 70 hours of flight time spanning the planet. To this day, it remains the stealthiest aircraft ever produced. While the F-117 was designated as a fighter, both it and the B-2 were exclusively penetrating bombers with no air-to-air capability. This narrow use of stealth technology would soon change. During the early 1980s, the Air Force would put forward a request for a new generation of air superiority aircraft, with stealth being a priority on the list of requirements. Unlike a bomber, the demands of a fighter aircraft are more intensive. They require speed, maneuverability, and powerful radar and sensor packages. These requirements all compete against stealth within a fighter design. Because of these compromises, stealth implementation in a fighter isn't about complete stealth, but rather being the first to detect and fire on a target. The F-22 was designed to be fast and extremely agile in air-to-air combat, utilizing powerful, supersonic-capable thrust vectoring engines and traditional control surfaces. It carried over low radar cross-section design cues from previous stealth programs, utilizing edge-shape refinements, a coated canopy, buried engines with masked inlet design, composite construction, radar-absorbent materials, and internal weapons base. Low radar cross-section was given a higher priority at angles in which it would face off against other aircraft, hindering easy detection and missile tracking. In addition, its stealth surfaces were designed to evade the smaller wavelength radar used by other aircraft. It also relied less on radar-absorbent material due to their higher maintenance requirements. Tactically, the F-22 makes use of sensor fusion, linking battlespace data from other aircraft and non-emitting sensors to avoid giving away its own position by radar emission. Overlapping with the F-22 program, work started on the F-35 stealth fighter in 1992. Design cues and technology from the F-22 made its way to the F-35. Similar techniques were employed for reducing radar cross-sections. Notable differences are the use of stealthier chines instead of leading-edge extensions for enhanced maneuverability, a wide duct engine inlet that masks rotating components, and the use of more durable radar-absorbing materials. Similar to the F-22, more focus was given to the radar wavelengths used by other aircraft and missiles. With the success and dominance of the US stealth program, the technology has worked its way into other applications. The cancelled Comanche RAH-66 reconnaissance helicopter, for example, was an attempt to employ stealth on a rotary wing aircraft. Other examples include naval programs such as the Sea Shadow and the USS Zumwalt. With unmanned aviation becoming the next frontier of combat aviation, stealth technology is also being incorporated into the next generation of unmanned air combat vehicles, as seen by the Grumman X-47B. With heavy air defense research being funneled into the detection of stealth aircraft and the emergence of competing stealth platforms on the world stage, the constant battle to stay one step ahead of detection will always be coupled to combat aviation.